Dear students, welcome back. In this session, we are going to discuss about the Faradic current, how the Faradic current is produced using some apparatus, and in the apparatus, what are the coils used to produce Faradic current. Okay, so now what do you mean by Faradic current? I have already mentioned in the therapeutic currents. Again, we will see. So the Faradic current is used for producing muscle contraction by stimulation of the motor nerves and was originally produced from a type of induction coil. The current provided by these first Faradic coils was an unevenly alternating current. Okay. Each cycle consists of two unequal phases. Here you can find two unequal phases. The first one, this one is first. The first one is low intensity, long duration, and the second one is high intensity and short duration. The frequency was approximately 50 cycles per second, and the duration of the second phase about 1 millisecond. Okay, this is the graph you can find here. This is the form of original Faradic current. Okay, so a number of different types of Faradic coils were developed, but only one of these are used nowadays. Okay, that is called as smart Faradic coil, and the current producers differs from the original one is that of a train of damped oscillations with a frequency of 1000 cycles per second follows each peak a high EMF. Okay. In addition, various types of valve operated apparatus have now been developed, producing currents that gives rise the same physiological effects as that of the original Faradic curve. And these currents differ considerably in form, but the essential features are impulses of a duration of between 0.1 and 1 millisecond repeated to 50 to 100 times per second. So these are the essential features for impulses. If such a kind impulse we can produce, then it gives the physiological effects of this original Faradic type of current. Okay, so a Faradic type of current is a short duration interrupted direct current with pulse duration of 0.1 to 1 millisecond and frequency of 50 to 100 hertz. Okay, so this is the introduction for Faradic current and how this Faradic current was produced previously. So the type of Faradic current produced by some of the coils, the first one is the Lewis-Jones Faradic coil and then Bristow Faradic coil. Okay, these are the two coils which are used for the production of Faradic type of current. And nowadays in the modern electrical stimulator they are using a circuit instead of these coils. That circuit is called as multi-vibrator circuit. So we are going to discuss about all these three apparatus which are producing the Faradic current. Okay, now first we will see the Lewis-Jones Faradic coil. Okay, yes, here comes the Lewis-Jones Faradic coil. This is the original type of Faradic coil, and although it is no longer used for the treatment of patients because as it illustrates the working of a simple induction coil. Okay, now if you see the circuit, the apparatus consists of two circuits, okay, one and two circuits. The primary circuit, this is called as primary circuit, and this one is secondary circuit. The primary circuit is supplied from a single Lagrange cell and consists of a switch and also primary coil and interrupting device wired in series with each other. Okay, this one is the interrupting device, and the primary coil is wired in series with each other. So the primary coil has many turns of insulated copper wire wound on a laminated soft iron core. This one is the soft iron core. Okay, the interrupting device, sometimes known as Wagner hammer interrupting device. So this one is called as interrupting device, and this is the primary coil. So these two are arranged in series to that of the Lagrange cell. Okay, so the interrupting device, which is also known as Wagner hammer interrupting device, which is consisting of a metal screw here, that is A. A is the metal screw held in a metal screw support, that is B, metal screw support B, and with its tip, so the screw is the tip of the screw is resting against the spring metal limb of hammer, so that is C. This is the metal limb of hammer. So the tip of the screw is resting on this limb of the hammer. Okay, one end of the hammer is fixed here, one end of the hammer is fixed, and the other has a soft iron head. So this one is having a soft iron head which lies opposite, and though it is not contact with the primary coil, and but the spring, that is metal limb, is connected to the primary coil. Okay, this is about the first circuit. Now coming to the secondary coil. So we have discussed about the primary coil now, and now we are going to discuss about the secondary coil. The secondary coil also of an insulated copper wire. Here it is having an insulated copper wire, but with many more turns than the primary. So the number of turns are more than that of the primary, and which is wound on a hollow wooden bobbin. So this one is wound on a hollow wooden bobbin which can be moved over the primary coil. Okay, and this one is having three terminals are connected to the secondary coil, one to each end and 1/3 of the way along. So at the ends of the secondary coils, it is having two terminals, and 1/3 of the coil is having another terminal. Okay, so this is the structure of Lewis-Jones Faradic coil. Now we will see the working of this Lewis-Jones Faradic coil. Okay, when the switch is turned on, current passes from cell through the switch screw support, okay, and from screw to screw limb of the hammer and to the primary coil and back to the cell. Okay. And as the current passes through the primary coil, a magnetic field is set up. The core of the coil is magnetized. Now the core of the coil is magnetized and it attracts the soft iron head of the hammer. Now this one is attracted towards the coil. Okay. So this one is going to touch the coil. Then what happens? Here the tip of the screw is having connection with this what you call as metal limb of the hammer is broken down here now. Okay, so then what happens? The current is going to stop to flow in this primary coil. Then what happens? So here it becomes demagnetized. Once demagnetized, again the hammer comes back to its position. Once it comes back to the position, the tip again will come in contact with the metal limb of the hammer. Now the circuit is again closed. Now again the current flows through this primary coil and again it is magnetized. After magnetization, this hammer is going to attach with this attracts towards this iron core. Then what happens? Again circle breaks. So like that it is going to occur. Okay, it is going to occur. This is called the series of events. This series of events is repeated approximately 50 times per second and an interrupted direct current flows in the primary circuit. Okay, this circuit has inductance. As the current varies, a self-induced EMF is set up. Okay, this opposes the rise of the primary current, so making it more gradual. When the primary current falls, the self-induced EMF tends to prolong the flow of current. Okay, that means tends to prolong the flow of current means it cannot do so to any great extent as the circuit is broken, but sparks pass between the screw and the hammer. Okay, so prolonging the flow slightly. Okay, so the primary current which is obtained by this Lewis Jones Faradic coil, in the graph we can see it is obtained like this. Okay, so there is some variation to the normal original Faradic type of current. Okay, this interrupted current flowing through the primary coil set up a varying magnetic field which cuts the secondary coil, inducing an EMF in it. So what happens if the secondary coil moves on the primary coil? Then what happens? So the magnetic field which is developed around this primary coil will cut the secondary coil, inducing an EMF in it. Okay, so based upon the Lenz's law, when the primary current is rising in intensity, the EMF induced in the secondary is in the opposite direction to that applied to the primary. Okay, so this one we have already seen in basic physics. Okay, while when the primary current is falling in intensity, the induced EMF is in the same direction as that of the primary. Thus, an alternating EMF is induced in the secondary coil. Faraday's law of electromagnetic induction states that the strength of the induced EMF is proportional to the rate of change of magnetic field. The primary current rises slowly in intensity, so the magnetic field changes slowly and the induced EMF is small. If it is induced, the primary current rises fastly, then what happens? Then the EMF is also more. Okay, so the primary current falls quickly, so the magnetic field changes rapidly and the EMF induced at the break of the primary circuit is much greater than that of induced by the rise of current. Okay, so for that reason we'll get such kind of waveforms. The secondary coils has many more turns than that of primary, so the EMF induced in the secondary is much greater than that of applied to the primary. Okay, so you can mention that. So the interrupted direct current flowing through the primary coil sets a varying magnetic field which cuts the secondary coil, inducing an EMF in it, and the resulting EMF we can see as in the form of waveforms like this. And the secondary coil has many more turns of wear than the primary, so the EMF induced in the secondary is much greater than that of applied to the primary. How can you regulate the current in such kind of coils? So the secondary coils is having 3 terminals, isn't it? And the terminals marked this second and third, which are connected to the patient, the whole EMF induced in the secondary coil is available. If terminals 2 and 3 are used, 2/3 of the coil are used and 1/3 of the total EMF is available. So for example, if 1 and 3rd terminals are connected to the patient, the whole EMF induced in the secondary coil is available. If 2 and 3 terminals are used, 2/3 of the coil are used and 2/3 of the EMF is available. While the terminals 1 and 2, 1/3 of the EMF is used. Fine regulation of the current is obtained by moving the secondary coil over the primary. As the secondary is pushed over the primary, it is cut by an increasing number of magnetic lines of force and the induced EMF is increased. As it is withdrawn, the EMF is reduced. So current from this battery was surged by moving the secondary coil to and fro in this manner. This is about the Lewis-Jones Faradic coil. In the next session, we are going to discuss about other Faradic coil called the Smart Bristow Faradic coil. Thank you.